This video is based on the Carnot cycle. So that is the first cycle that we will be looking at. So yeah, we will have Carnot cycle. So that means in the ideal gas cycles, we'll be looking into Carnot cycle. Then we have Otto cycle. Then we'll be looking into Brayton cycle or Joule cycles, or sometimes it's known as the constant pressure cycle. Then we have diesel cycle, and then dual combustion cycles. So these are the 5 cycles that we'll be looking at in this chapter 1. So here, basically the first thing that I need to do is to teach how to construct the TS and the PV diagram for Carnot cycle. So in the Carnot cycle, we have 2 reversible isothermal processes and 2 reversible isentropic processes. So here, first we have the TS diagram. So since we have 2 reversible isothermal processes, and this is a T against S graph, so what you need to do is to draw 2 horizontal lines across. And since there's only 2 temperature lines, so the higher one refers to the higher temperature, which is based on the source, and the low temperature, which is based on the lower temperature region, the sink. So then we have 2 isentropic process that appears as a straight vertical line on the TS diagram, and at which you have the entropy from one point to another. So here we have 4 intersection points. So each of the intersection point, we just mark it down. So we have 4 points. So we start with point 1, 2, 3, and 4 in this order, because the heat engine cycles usually goes in the clockwise direction. So this is clockwise direction. Then we move on to the PV diagram. So the vertical axis as the pressure, and the horizontal axis as the specific volume or an absolute volume. So we have to draw 2 constant temperature lines on the pressure volume diagram, the PV diagram. So this will be the 2 constant temperature or isothermal curve that we have drawn on the PV diagram. Then followed by 2 isentropic or 2 constant entropy line. So again, here we have 4 intersection points. So just mark down each intersection point. So these are the 4. So since we have 4 intersection points here, so there will be 4 processes. Remember, that consists of 2 reversible isothermal processes and 2 reversible isentropic process. So we have the point 1 should be located at the lower left-hand corner. The lower left-hand corner, which is point 1, which is at the lowest pressure, and of course the lowest temperature. And then from point 1 to 2, as from TS diagram, we can see that point 1 to 2 is an isentropic process, which is shown as a straight vertical line from 1 to 2 on the TS diagram. So therefore, we can locate the point 1 to be at the left-hand corner of your PV diagram. So that is your point 1 followed up by point 2, 3, and 4. So here you have the volume. Sorry, that is V2 and V4. That's my mistake. So clockwise direction. So you have the clockwise direction. So they moves in clockwise direction, both in TS and in PV diagram. So remember, for heat engines, the flow should be in clockwise direction. But then if, let's say for example, later on in the later stage when we do refrigeration cycle, the direction of rotation would be the other way around, that is anti-clockwise. So that is in clockwise direction. So that is your TS and PV diagram for Carnot cycle. So here, basically I have shown you with some animation from each of the state point, and also each of the process that involved in the Carnot cycle. So during the first stroke, we consider a piston cylinder device which is perfectly thermally insulated, because on this first stroke here, that is from point 1 to 2, we consider that the process is adiabatic or is isentropic. So we have to consider that is perfectly thermally insulated. So here you have the flow from state point 1 to state point 2, and that is an isentropic compression process, and it shows that the pistons is moving inwards towards the head of the cylinder. That is the first stroke. So the fluid is compressed isentropically and work is put in and no heat occurs, no heat transfer occurs. Work is put in, that means it is compression, work input. So the second one is when it goes from point 2 to point 3, state point 2 to state point 3, where it undergoes a constant temperature process. As you can see, when the arrows move from point 2 to 3, that is an increase in entropy. Means it shows that it's a heating process. So it's an isothermal heating process from point 2 to 3, whereas point 1 to 2 is an isentropic, that means no heat flow. Okay, isentropic compression process. 2 to 3 is an isothermal or constant temperature heating process. So the pistons moves from the state point 2 backwards, that means moving towards to the state point 3, and in this case it is not perfectly thermally insulated. So you have the fluid is heated isothermally. This could only occur if it is heated as it expands, so work is taken out and heat is supplied to the system. So here there is another two diagram that is based on state point 3 to state point 4, that is the third stroke. So the pistons will be moving from state point 3 backward, that means towards the state point 4. So you have this. So in this case, the fluid continues to expand isentropically with no heat transfer. Work output is obtained. So in this case, again, the cylinder is perfectly thermally insulated. Then you have the fourth stroke, that is from 3 to 4. 3 to 4, where as you can see in the TS diagram, 3 to 4 is the previous one, that is isentropic. Now this is from state point 4 to state point 1. So the pistons will be moving forward again from the state point 4 back to the original position, point 1. And on the TS diagram, you can see that from state point 4 to state point 1, this is an isothermal process and it is not an isentropic process. And remember, from point 1 to 2, no heat flow, and 3 to 4, there is no heat flow. From the TS diagram, you can see. So from 2 to 3, you can see there is an increase in entropy. That means it is a heating process. And from state point 4 to 1, it is a cooling process. So here you can see the pistons is moving from state point 4 to state point 1. And the cycle goes in the clockwise direction. So the fluid is cooled isothermally. This can only occur if it cools as it is compressed. So work is put in and heat is taken out. At the end of this process, everything is restored to its initial condition. This is Carnot cycle. So based on Carnot cycle, closed system, to be an engine, work out must be larger than work in. That means the work output, the energy work output, or the work done by the system must be larger than the work done on the system. So work out must be greater than work in, and the net amount of work is obtained from the cycle. So you can see the TS diagram, both the TS diagram below. You can see the first TS diagram shows you the Q net, or at the same time, we can say that is also the W net. So returns back to second law or first law, there is a law stated, the second law stated that, okay, Q net equals to W net. So that is Q net, and that also can be equals to the W net network. It also follows that since the area under the PV graph represents work done, the area enclosed by the PV diagram represents the net work transfer. It also follows that since the area under TS graph or diagram represents the heat transfer, then the area enclosed on the TS diagram represents the net heat transfer. So this is true for all cycles and also for all real engines. So net heat is equals to net work. So from these three TS diagrams that I've drawn, the first one based on Q net. How to obtain the Q net is by taking the area under the process path from state point 2 to 3, which is equals to TH, multiplied by the base of S4 minus S1 or S3 minus S2. Then you take the area QS, the total area under the process path of state point 2 to 3, minus or deduct or minus the other TS diagram, which is based on state point 4 to 1, which also representing, okay, the area of heat rejected heat that is under the process path from state point 4 to 1. So from there, you will be able to obtain the net work, or the net heat flow. So that is QS formula that is based on the area under the process path from 2 to 3. And since S3 is equals to S4 and S2 equals to S1, so it can be written as S4 minus S1 as well. So this is heat rejected. And we know that Q net, excuse me, Q net is equals to QS minus QR. QS representing the heat supply and QR is the heat rejected from the system. So from here you have this formula, and based on second law, we know that net heat equals to net work. So we have this. Okay, so then we have net work is equals to the same formula as what is shown for the Q net. So here, for the change of entropy for the isothermal process, remember in the section part 1b, I have shown you the formula for the change of entropy for an isothermal process. Please do refer back to section 1b. The table I've shown you the change of entropy during an isothermal process, and it is written as this, or it can be written as V min over V max actually. So from here, the Carnot efficiency, as we know, all efficiency or thermal efficiency is defined as desired output over required input. So the desired output in this case is the work net, and the required input to be the heat supply. So we have net work out divided by heat supply, the thermal efficiency or the efficiency of the Carnot cycle. So you have this for work net. Okay, so you have either this or that. So from the thermal efficiency, you have this, and from there, you have the work ratio. For this part, we will be looking at work ratio. So work ratio is defined as the ratio of net work to the gross work expansion. So whenever we refer to work, definitely we will be referring to the PV diagram. So since they say gross work expansion, that means we will have to refer to all the expansion processes that is in the PV diagram. So here it is shown that the expansion process is from state point 2 to 3 and from state point 3 to 4. So actually, okay, so both these actually refers to a curve. It's not a linear line. That is for the convenience of my work. So it is a straight line. So from here, okay, so you have work ratio is defined as net work over gross work expansion. So the gross work expansion is the total work expansion that we have, that is from work done 2 to 3 and work done 3 to 4. So when you add both of them together, you will have the gross work expansion. So from state point 2 to 3 actually refers to an isothermal expansion where the heat flow, the internal energy changes, the internal changes is equals to 0 during isothermal process. Remember, that is based on the Joule's law. So you have this, okay, or you have this. Then 3 to 4 is actually an isentropic expansion process where the change of entropy is 0. Remember, isentropic represents constant entropy, or adiabatic refers to Q equals to 0. So in this case, you don't have heat, but you have work output based on the PV diagram. So we have work is equals to this since the Q is equals to 0 based on non-flow energy equation. So you have this or this. Okay. So the next is the mean effective pressure, and is defined as the network output divided by the length of PV diagrams. The length of PV diagram here is basically the length or the volume, the distance between the innermost and the outermost point on your PV diagram, because it's referring to the PV diagram. So you take the difference between V4 and V2. That would give you the length of the PV diagram. So the network out basically is what we have already considered earlier. And the length of PV diagram would be V4 minus V2. This will give you the mean effective pressure. So basically this part here, I'm showing you, okay, all the important points or the important things that you would have to look into. First, the thermal efficiency. Second, the work ratio and the mean effective pressure. And of course, to know how to construct the TS and the PV diagram for the Carnot cycle. So this is the exercise. So the solution or the working of these two problems will be shown on the later slides. Thank you very much for now.